Is my screen visible?
Yes, we can see.
Okay, thank you. So, let's start. So, yeah, in this session two, we'll focus on one or two topics that were taught in week two, basically. So, the most significant thing that you were taught in this week was actually edge detection. So, just pardon me, I have to do this. Yeah. So, edge detection. So now the question comes to mind, why do we need to do edge detection at all, right? And what is edge detection? So basically you can see that if you look at this image, what do we mean by edges? Edges are these sharp things. Basically in layman's terms, edges are basically boundaries of objects, okay? And yeah. So why do we need to detect edges in images? So imagine you are a human being, you are looking at an image, say suppose an image like this, or even if you look at your surrounding, how do you suppose you detect objects in that image? So what you do, suppose you have a book in front of you. What you'll do is you'll try to perceive that there's a rectangular structure where there's a height, width and depth. Okay. So in order to understand the shape, you are basically looking at the edge of the object. I mean, in the backdrop of the background. So similarly here, to understand what's going on in the image, you see that what we are looking at is something like this. There's a circular thing here, then there's another circle inside, and so on. So this is how we understand objects. This is how we perceive objects. And because image processing, whatever techniques that we are seeing, these are similar to how we perceive things. That is why edge detection is one step where the machine. We are basically trying to make the machine understand what objects are there in the image, what is going on inside the image. So we'll show you some very basic edge detection algorithms and walk you through some code maybe, which will give you an understanding of how we are doing this. So what we want is, given an image like this, which is a real life image, which has objects in it, which has different things going on in it. What we want is something like this, where which is kind of, you can think of it as a binary image, which gives you the boundaries of these different objects in the form of this. So you can see that even by looking at this black and white image, you can understand what's going on. That is because you have been already given the edges inside it. So this is what, from here we want to go here to detect the edges. Question is, how do we do that? So we'll focus on. So there are two techniques that I'm sure you have gone through by now, which were taught in the second week basically. So one is maxima or minima detection. So why do we use maxima or minima detection? Because what basically is an edge? Edge is basically, suppose you are inside this particular. Okay, this is maybe not the best thing. Okay, so yeah, suppose you are inside this particular black circle. Okay, and now when you are going towards the edge of it, suddenly after you cross the edge, something different happens. We are inside this some other brown circle maybe. So that is why, what does edge, how do we identify edges? Edges happen when there's a sudden change in the intensity of the image. So how do we measure such intensities? How do we measure such changes in intensities? We can find derivative, right, in the image, and whenever there is a increase or decrease, that is wherever there is a maxima or minima, we can say that we have found an edge. So that is why maxima, minima detection, then second derivatives. I'm sure you have gone through all of this. So all of these are used to detect edges. So let's look at a very simple case. So I'll, yeah, do this as slideshow. Yeah. So what we are trying to do here is, so this is a Sobel operator. So Sobel operator. So what we are trying to do is, given these sort of images, we'll construct filters, linear filters like you saw, or filters basically, which will try to detect what is going on in the image. And how it will try to do is, as I said, it will try to measure where there's a huge difference in uh, Okay, so just give me a second. I'll be back. I'll just join from my phone also so that anyway, let's continue. Let's yeah. Okay, so I hope this is visible to you at this point. So what is a Sobel operator? Sobel operator is basically a filter, which, as I said, is measuring the difference in the intensities between an edge, right? Intensities to the left of it and right of it, or to the bottom of it and above it. So that is given by these two filters basically. So here you can see that this type of a filter, when you operate on an image, it will basically say that, like, how different are your intensities, I mean, with respect to whatever filter, whatever pixel location you are at, it will measure how different are the pixel intensities to the left of you and to the right of you, and that will basically give you kind of an idea of whether there's a sudden intensity change or not. So suppose, uh, take this image for example. So here you can see that, I mean, the values are all 100 here and 200 here. That means what? That suddenly there has been a change from 100 to 200 in this. So see, all here it was all, this was 100, 100, 100, that's fine. 100, 100, 100, no problem. Then suddenly here there was 100 and this changed to 200. This changed to 200 and so on. This means what? That there's a sudden, this intensity change indicates that there is something going on here in between these two. So there must be some edge which is lying here, which is leading to this change from this 100 value to the 200 value, right? So how do we detect it? Suppose this is our central pixel location, and we want to convolve this particular filter on top of this. So this particular filter sits here in this whatever window that I am marking, where this is the central pixel location. And see here, it has already calculated. So -1 into 100 plus -2 into 100 plus -1 into 100 and so on. So we calculate this entire thing and we see that the value turns out to be 400. Yeah. So this means what? That this value is quite large, which kind of shows you that, okay, there's a bit of a something going on. So some change has happened over here. So because of which the value is actually high, the value returned by this filter at this particular pixel location. This kind of tells you that, okay, so there's an edge going on here, right? And similarly, there's a GY, which is a Y direction operator. So this basically, the X direction basically measures vertical edges, whereas the Y measures or horizontal edges. So you can understand by looking at the structure of this. So uh, here it's like all the values are lying to the left and right, and here it's bottom and top. Sorry, top and bottom. So if you place it here, then you'll see that. So for example, here, how do we understand that there is a vertical or a horizontal edge? What do we do here? Well, let's try to place this particular y direction Sobel operator on the same pixel location. So what you'll do is, so basically this is 100 into plus 1, 100 into plus 2, 200 into plus 1. And here it will be 100 into minus 1, 100 into minus 2 and 200 into minus 1. All these are 0. So inherently what you will see is that these values and these values, they will cancel out. I mean, after superposition with this particular filter, and you'll get a 0 here. Which means that here, if you think of it in the horizontal way, there's nothing to be nothing suspicious going on. So no edge is there. So that is how. So basically, this is why this particular filter is used for detecting vertical edges, and this is for horizontal edges. Now question is that, okay, in the image in real life, obviously all edges, it's not a beautiful life, so all edges won't be horizontal or vertical. So um, things would be going on in between also. So what if it's slanted towards the right or slanted towards the left, or anything different? It's an edge, but it's something different. So just if you look at this image, we don't hardly have any true vertical or horizontal edges. So how to capture edges which are somewhere in between? It's through this formula. So basically, you are capturing the x direction and y direction, and this is how this we do it in this form. So gx square plus gy square, a root over of that. So that kind of gives you edges that are in between the horizontal and vertical, and you also can get the angle, the yeah, so the angle of the edge, the orientation of the edge as we call it, so by using this sort of a formula. So this is basically tan inverse of gy by g of x. So that basically gives you so these two kind of give you the magnitude of the edge and the angle of the edge. So some examples, let me do a slideshow here. Yeah. So this is a table. Now table is there, chair is there, and so on. And now what we want to do is we want to find out edges here. Okay. So I don't know whether this is visible or not, but this is the y direction Sobel. This is the image that you get after operating on the y direction, and this is the one that you get after operating on the x direction. So can someone unmute and tell me like what is going on? I mean, do you see whether there's a difference between these two? Anyone?
Yes, ma'am. In the first picture, the horizontal edges are more prominent, and in the second one, vertical edges seems to be more prominent.
Correct, correct. So that is exactly what I said. So y direction Sobel operators are good at identifying horizontal edges, whereas x directions are good at identifying vertical edges. So this is what happens. So when you are trying to use individually each of them, this is what happens. So you get the edges, but you get them in an incomplete way. So now what you do is just by doing this, you see that if I hope this is visible to you, you'll see that okay, most of the edges have come up, which were not, which were missing in some sense in these two images. So most of them have come up. So that is why we require this transformation to get hold of basically all the different orientation edges. So cool. So this is very simple. Sobel operator. So if you look at the literature, if you look at the books that are available, you'll see that there are multiple variants of this kind of an operator. So there's Prebit, and I think there's something called Robert, and there are many other operators, and there's this one also. So Laplacian, uh, uh, Laplacian of Gaussian, they are also used to detect edges. So this is just to give you a feel of what's going on. And now one thing we can do is yeah, let's go through the code of, okay, this, yeah, let me walk you through the code of this Sobel operator, how it looks like and all. Yeah. So let it keep connecting. So yeah. So what we do here is first of all, obviously again we import all the modules as we had discussed last time. So NumPy, CV2 is basically OpenCV, Matplotlib, etc. We
Ma'am,
first.
it's not visible. I mean, the font size is very
Is it
small.
better now?
Yes. Thank
Okay.
you.
Yeah. So now what we are trying to do is we'll first, so as it says here, it's all kind of written, so that's good. So what we want to do is we want to read any image. So again, the idea is that so I'll share this with you in a few moments, but the idea is that you can do this yourself by inserting any image here. So all you need to do is give the link. So now what happens here is that you just read the image. Yeah. So, oops, yeah. So you just read the image, and then all you need to do here is convert the image to the black and white, to basically grayscale. So grayscale, they have used a different, you can do it either directly through matplotlib's functionalities that are available, or you can do it in this way also that they have shown. So you get hold of each of the channels, the R, G, and B basically, and then you do some linear combinations of them to get the grayscale image. So this is the original image, and this is what it looks like after converting to grayscale. So now let's come. This is an easy part. So we'll apply the Sobel operator here. So what goes on here is, so Sobel, as I said, it looks very simple. It looks something like this. So 1 to 1 on the left, minus 1, minus 2, minus 1 on the right. Similarly, 1 to 1 on the top, and minus 1, minus 2, and minus 1 on the bottom. So just what you do is you use NumPy to store these matrices in the form of NumPy arrays. Then what you do is you take the grayscale image. So grayscale image is basically the one that we converted to grayscale. So input image is the original image, and grayscale is the one that is converted to grayscale, of course. So now you basically what you do is you have a Sobel filtered image variable, which is nothing but an empty image sort of. You can think of it like that, which is of the shape of the input image, basically the grayscale image. And now what you need to do, given these two filters, all you need to do is convolve them with the original image, right? So this convolution operation is kind of given here. So this is a naive way of doing it, but if you look at the code, you'll understand that this is inherently what we do. So
Ma'am, I have a small doubt regarding the definition of this GX and GY.
sure, tell me.
That just showed the slides on which you defined
Okay.
GX and GY. Yeah.
Mm-hmm.
So here in GX, it's already convolved with this image part A,
Uh,
the coefficients.
yeah. See, these are all different. Yeah. In this case, it's convolved. But yeah, you can
Ma'am,
define these are just variable names. All right. So
so
yeah,
if it's already convolved, then this means this is the response.
correct, correct.
So if we are already having a response, then again convolving it with the image.
No. So yeah, so you can what we are trying to do in the code is just taking this filter, this 3 cross 3 filter, and now we'll convolve with
So,
the image.
yeah, exactly. So, what we are defining to be the Sobel operator, is it without A or with
No,
A?
it's the without a. Yeah,
Without A, okay.
yeah.
Means GX is excluding this A.
Correct. Yeah. It's actually shown here as if it's convolved with A already. Yeah.
Yeah,
So
exactly.
yeah. So actually no. If to clarify your doubt, in this case, sorry, it was my bad. In this case, it was obtained after the convolution only. This GX and GY,
Yeah,
but the
but still,
operator,
yeah, yeah.
they are the responses, as you are correct. But the operator, if you think about, it's this. So this
Only
is
the
the
part under the matrix.
correct. It's the filter. So this
Hmm.
filter is leading to the edge detection,
Yeah,
right?
exactly.
So
It's clear now.
yeah. So that is how it's said here. So they are calling this in this particular code. They are calling the filter as GX and GY.
Hmm.
So correct. So now what they are doing is simply they are doing a convolution, which means that they are multiplying this g of x with the particular window in the grayscale image. So something like this. So they are picking out the window from here, and they are convolving the individual Sobel operators with those particular windows to get the convolution values. So that is what is going on here in this small gx and small gy. And what they do is, so this finally we had created this Sobel filtered image, which was empty initially. So what we'll do is, in the pixel central location, center pixel, we'll put this value. So it's like this again. So if this is the central pixel, then its value will be given by this gx square plus gy square. I mean after the convolution. Right. So this is where this is the code also is simple. Simple. You can go through it on your own time, but this is a very naive but a good way of understanding what the convolution operation does. Okay. So now what we want to do is, obviously we want to see what we created. So let's that is why they have plotted this, the input image first and then the Sobel filtered image. So this is how the input image looks like, and I hope this is visible to you. But yeah, these are all the edges that got detected by the Sobel filter. So yeah, so it's a very simple operation. So most of the filter these operations using Sobel, Previt or other filters are just like that. So the same code will work for all of them, just that you have to change the structure of these two. So this is what more or less edge detection using Sobel detector looks like. And now, very small walkthrough through what we learned in the. I mean, this is another thing that we learned in the last week, Canny edge detector. So this is a little bit more sophisticated form of, basically an edge detector algorithm. So the steps here are actually given below. Now, can anyone tell me like, okay, yeah, so the steps here actually are given below, but let's go to the first step first. So apply Gaussian filter to reduce the noise from the image. So now, can anyone tell me why we would need to apply this step? Why suddenly Gaussian filter came into our lives? Can anyone tell me?
Because maybe the filter will pass this noise also if we don't smooth it.
It will detect the
Correct.
edges as well as it will
Correct.
detect the noise as well.
Noise. Correct,
Yeah.
correct. You are right. So what it will do is these type of filters, what they'll do is they also detect. So if real life images won't be as smooth as whatever is shown here, so it will be very very distorted. There will be a lot of noises, and the problem with these filters is they are very very sensitive to noises. So they'll pick up those noise values and they'll detect them as edges. So that is why the first step that is carried out in canny edge detection is that you first smoothen everything. So just apply Gaussian blur to smooth the image, and that will get rid of the noisy parts basically, and then we'll see how to get back to the original image from here. So Gaussian filter, applying a Gaussian filter is not, it's kind of quite easy. So this function does that. So all you need to do is, as I said, so we know that Gaussian filter is defined by something like this. So yeah, so it's like exponential of minus x square plus y square divided by 2 into sigma square basically. Yeah, so this is what the this thing looks like, the Gaussian filter looks like. And all you need to do is you need to all you need to do is you need to this gives you the Gaussian filter of a fixed size. So
And sigma is the noise variance of.
sigma is the variance of the Gaussian. So as and when I'll show you an example later, but in the slides it's there. So if you go on increasing sigma, the image will become more and more blurrier. So you can try this out by yourself also. So all you need to do, again, as I'm saying, in order to understand what is going on here, the best policy would be to run these things on images of your own. So I told you I'll share this link, but I forgot. So oops, let me share this one.
Just a small question, ma'am.
Yeah.
Yeah, actually, like as you are showing the coding, so what would you suggest for the beginner who wants to do coding for the CNN and PySpark or TensorFlow? Which one you suggest to the beginners, especially in this domain?
So for beginners, for CN, you mean for neural networks, right?
Yeah, CNN or this image processing kind of things
So
where so
image processing, yeah, image processing is separate. You can use NumPy. Then there are other libraries like skimage, OpenCV.
okay,
Then yeah, so many things are there. So all of them are quite simple because whatever we are teaching here, you will find them ready-made in those libraries. So
yeah,
those are
understood.
good for that. And for neural networks, at this point, so when I used to learn, I used Keras basically, and
Mhm.
yeah, so Keras would be a good starting point because it's simple to see and understand. You don't have to do much, and you'll just add lines of code, and models will run. And I think there's another one called PyTorch Lightning. Even that I
Mhm.
have heard that it's simpler. So
Okay.
for just the beginning steps, it's better to start with these two. But as and when you proceed, you should learn TensorFlow and PyTorch for
Okay.
research purposes and all.
Thank you. Thank you. Much
Yeah.
appreciated. Thank you.
Okay. So correct. So where were we? We were here. So yeah, so we have an image like this which we have read. So again, you can replace this with any image of your own, and you can run them and see what's going on. So this is how the image looks like. So we have already automatically converted this to grayscale, right? And now let's okay. Hmm, yeah. So now what we have done is, now we convolve the image with the Gaussian kernel that we created, where this kernel is of shape 5 cross 5 here. So we are defining the shape here. So accordingly it will create the Gaussian in this way. So correct. Now that we have convolved it, now just look at the difference between the two images. So it is now while the original was much sharper, now everything has become much more blurrier. But in the process, we have got rid of much of the noise that was there in the image. So now it will be easier for the edge detector to detect the edges from this kind of an image. Now that there is no noise in it. Okay. Yeah. So now next step is we again use a Sobel-like operator to detect edges from this smoothened image. So again the same, almost the same code that we saw here, just that we are, instead of using our own, convolution function, here we are using some predefined functions from some libraries which you can find here. So SciPy, from SciPy import ND image. So there's a convol function where you can directly do the convolution, and whatever you do the other whatever math was there to find the final uh, magnitude of the final image and the theta, the which is the orientation basically. So now this is the function which does the Sobel filtering, and then what you get from here is the final edge map, the edge based image, and the orientation in this gradient mat and theta mat. So by running this particular function, and now this is how this looks like. So the Sobel returns something like this. Okay, I don't know why it's hanging so many times for me. Just give me a second. Yeah. So these are the two pictures, that two images consisting of the edges first and then the orientation. So this is what Sobel does. But again, let's go back at the steps once. Mm, yes. So what did we do? We did a Gaussian blurring first, and then we found the magnitude and orientation of gradient. So next step is non-maximum suppression. So what do we mean by non-maximum suppression? So we'll look at some examples here. Yeah. So again, as I said, that images are not only noisy, but they'll never be like this. Okay, so there'll never be a single point of, I mean, what I'm trying to say is that an edge won't be that thin that it will be just lying in in this particular column of pixels. So an edge can basically consist of many columns of pixels. So this entire, maybe these all these four columns can consist of an edge. So an edge, in what I'm trying to say is that it can be very broad. So it can be something like this. Um, yeah. So suppose you have this kind of an image, and your edges can be something like this. So it can be very wide. So this edge, if you can see, It's not just one line. And you can see, if I can, yeah, yeah. When I zoom this, you'll see that this particular value this is 1 pixel in the image. So you can imagine how many, pixels this edge is consisting of in total. So that is the problem. Oops, sorry. Yeah, that edges are not really as simple as we think. They are spread across many pixels, but we still have to detect them. So what we need to do first is get rid of all these things that are, we want basically a true edge this time. We want a line, or we want to make it more finer as we go ahead. So we want to get rid of these, blurry parts, and we want to get a straight line for this. Or not a straight line, but we want to get a true edge for this, which won't really spread across so many pixels. We want an approximation for this, and the way to do that is something like this, that you have an edge. So given something like this, you find the direction, which is the tangential direction, not the tangential, it's like the normal direction from the edge, the orthogonal direction. So you find the orthogonal direction from this edge, and at a given particular pixel, basically, so take this pixel, the one that is marked in red, and you find the orthogonal direction from here, and then you find out, so based on the direction of the edge, so whatever direction is returned by your direction filter, so find out the orientation of this pixel. So then that will give you something like this, some normal vector like this. And now you'll traverse across this, all these values that are there around this particular central pixel. So I mean, which is shown by this circle. So if this is the central pixel, the one that I'm pointing at, you look at the pixels that are around you, and then you try to find out which is the maximum value. So if your pixel is the maximum one in terms of intensity, then only you keep it. Otherwise, you throw it away. Okay, so that is what it says here. That check if pixel is local maximum along gradient direction. Could require yeah. So what it's trying to say is basically you create a not a window, but you try to find out a neighborhood across your around your chosen pixel, and from there you'll try to see if your chosen pixel is basically so where were we? Yeah, there you'll try to see if your chosen pixel is basically the maximum or not. If it's maximum, then only we'll retain it, right? So I mean, this retaining, this looking at the neighborhood and this retaining of the maximum value, this is what is meant by non-maximum suppression. So yeah, so I'll just show you one other slide that will make it a little bit clearer. Oops, this is uh,
Is it the only method for this fine edge detection?
no. So as I said, Sobel also is a edge detection method. So Canny is
No,
a
no, 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 not about Sobel and this one.
this
Yeah,
non-maximum suppression.
non-maximum suppression. I mean, can we use this averaging also after this, or some median filter along the edge only, so that this the layer becomes very thin, the edge?
No, I mean, I'm sure you'll find problems with that, because this is the one that we generally use for yeah, for detecting edges. So for basically the purpose that I'm saying, that so the end result will be something like this. So you had uh, what broad thick edges in this image, and now what you are trying to do is you have approximated them with this. So basically what you want to do is even using a median filter also, I think it won't be possible, because what you want is, say suppose you have this particular pixel, any pixel here.
Mhm,
So what you want is you have to get the maximum value from its neighborhood, right? So that is why,
mhm.
and the neighborhood also you have to make sure that that also is part of the edge. So those functionalities are all done by
I
the
mean, I mean just repeating application of this filter over the edge also.
uh,
That
can
will narrow down the this. Yeah,
uh,
first determine the edge, and
yeah.
over that thick edge, if we
Hmm.
apply this filtering again, Sobel filtering. Because
Uh,
what actually this is doing is extracting this based on the contrast, it's extracting the boundaries in this edges.
right. Yeah.
So if we have a thick edge, then we
Hmm.
apply this the same process on that thick edge, only on
Hmm.
that white portion.
Correct.
So from that also it will extract the make it thinner. So
Mm,
It won't change, right?
yeah, that's what.
the
So,
thickness will change
How?
because we are instead of considering this black and white, just consider it as shades of white.
no, but that
Suppose suppose we have
again,
a
again.
pixel.
So if you think of it, that is where Sobel and those operators will lose out because you see, I'll just
Because
share back my
because they are,
screen.
yeah, they are very sensitive to pixel values. So if I have a pixel at say around 200
Hmm.
and I have a pixel at 250 55,
Hmm.
so naturally Sobel operator will separate those two pixels also, although
No, so
in initial approval.
there's a thresholding available, no? So for Sobel. So you have to
Hmm,
set the thresholds. I mean, suppose you set what you are saying, I understand. So let's go back to the picture. So suppose you have so what you were saying is that you do non-maximum suppression over here. So that gives you something like this. So on
yeah.
top of that, you are saying that do Sobel
No,
again,
no,
is it?
no. Instead of this non-maximal suppression,
Hmm.
if we apply this Sobel filter again, just on the edges part,
Okay. Where were we? Yeah.
means after edge detection, if we have 2 3 pixels within range 200 to 255,
Hmm.
3 or 4 pixels, we can say the edge thickness
Yeah.
maybe 3 or 4 pixels.
See, I mean, see, Sobal, if we look at the where did the filter go? Uh, yeah, if we look at the filter, so
Hmm,
this the only step is not to convolve, okay, convolve with the image. There's another
hmm,
step where you decide, suppose here in the picture that I showed, so this value is 400. So nobody told you from beforehand that this 400 amounts to, I mean, this indicates an age. This has to be determined from before, that if suppose your convolved value is greater than a threshold, then you are an edge. Okay, so for example, you have, as you were saying, this is suppose 200 and this is 255. Then
hmm,
if you keep the threshold like this, that if, I mean, for example, if the difference is just so less, so 200 and 255 only, even then if you are detecting edges, then you'll detect a lot of edges, so which are
hmm,
not really correct edges, so there will be again noise. So you have to set the threshold in such a way that you detect edges properly, but you detect as much I mean as small amount of noise as possible. So all these things also have to be considered. That is why
Actually,
you do not.
yeah, in the code there was no option for threshold in the Sobel operator,
Okay.
so that's why I got confused.
But you have to do some sort of thresholding. Otherwise, for example, suppose this was, say, this was instead of 100, this was 1111 and 2222. So there's hardly any difference between 1 and 2. So you have to understand
Yes, yes.
somehow that what you will call as an edge and what you will not call as an edge. So if the here the difference is a lot, there are 400s and 4200s. That's why it's a big difference.
Uh,
But if that had
yeah,
been four ones and four twos, then you
yeah,
couldn't have called
exactly.
that an edge.
Okay.
That is why
So
you can't.
can you show me the threshold code part of this Sobel operator where we have
Yeah,
defined
yeah,
this
I'll
thresholding
just see. Yeah, yeah, yeah.
in the code?
So well filtered. Yeah, there was something I forgot this. Okay, I'll check and let you know. Okay, let me
Mhm.
proceed from here. But there's a,
Sure.
yeah, yeah. So I'll check it and let you know.
Okay,
Right.
thank you.
Yeah. Okay. So, yeah, where were we? Yeah, we were here. Mm, yes. So non-maximum suppression is what? what we are trying to do is we are trying to suppose looking at this particular image. Mm, yeah, so the direction of this particular this edge pixel can be anything. It can be this, it can be straight, it can be vertical like this, or anything. So you can't do it for yeah, you can't do it for all 360-degree angles, right? So what people do is they have divided the angles into bins. So suppose, since this is like this, so there can be a bin which is, suppose we take this as the this horizontal line as the 0 to 180 degree line, and this is approximately 40-45 degree you can call. So what we can do is we can divide this entire circle of 360 degrees into, suppose 4-5 bins. So it looks something like this. Okay, so you have a this being your central pixel, you have anything, I mean, you basically, this circle is there of 360 degrees, you divide them into bins like this. So if this is angle 0, then from here to here this is one bin, then here to here, so this is probably 30 degree, 30 to 60 is one bin, so 60 to 120 is one bin, and so on. So whatever, so you give each bin a number, so 0, 1, 2, 3, and so on. So what you'll do, what will happen is, suppose your central pixel is this, and the edge direction is somewhere along this line, somewhere in between, somewhere something like this. Then what happens is you basically say that your edge direction falls within within this bin one, and what then happens is that if you look at the window around it, around this edge pixel, all you have to do is look at the diagonal elements in that. So in this image, it amounts to something like this. So from here, since this falls, if you translate this to this particular circle, it falls in this bin 1. It looks like 45 degrees. So 45 degree, you can see it falls in bin 1. So yeah, it falls in bin 1. So then what you do is, if this middle one is your pixel location, you look at the diagonal elements in that window for your yeah for as your neighbors basically. Similarly, suppose if your edge direction is somewhere around in this particular uh, this particular bin, which is the bin 2, then what you do is you look at the top and bottom neighbor. Similarly, if you have this particular bin, you look at the left and right neighbor, and so on. So basically, this is how you divide the 360-degree bin into 360 degrees into some 3-4 bins like this, and then you accordingly you choose which neighbors to compare to in order to get the maximum, compare the maximum intensity. So that is kind of what is done over here. So you take the image, and then you have already computed the angles of the image, and now what you do is you consider these bins. So if it's 0 to 22.5, the angle is between these two, or 157.5 to 180, then you consider some, maybe this is probably the top one and bottom one, top element and top pixel and bottom pixel with respect to your central image, central pixel location. Similarly, there are other windows also, you can go through them. So as I said, looking at this particular circle, you can find out what are the particular neighbors whom I'll compare. And now what the rule is? The rule is that if I am greater than my neighbors, then I'll be chosen as an edge point, right? So now you can see after applying this non-max suppression, it's like so previously, just to give you a comparison of the, this is actually shrinking for me. Yeah. So this is how it becomes. It's very, very less visible. But now what you have done is you have gotten rid of the thick edges, and what you are left with are basically very, very fine edges. So that is step number 3 in Canny image detector. And now what is step number 4? So yeah, let's walk through it. So in step number 4, what we see is that, suppose If you here we do NMS, non-maxima suppression, and we have suppressed many of the edge points, many of the edge pixels, and because of that, somehow somewhere we are losing some information. So we'll try to build them back once again. So whatever information we have lost, we'll try to get that back through this idea called hysteresis thresholding. So there's a very typical algorithm for it. So suppose when you are you look when you look at the entire image, entire edge map, and basically you have the gradient magnitudes for them. So you look at them, and as I said that, so here there are two thresholds. Basically there's a high threshold and a low threshold. So if you're, but suppose you have a particular pixel, and if the threshold value, if the gradient magnitude for that pixel is actually greater than the high one, then you can, so it's all written here. So if gradient at pixel is greater than the high threshold, then you are sure that that's an edge pixel. Okay. And similarly, if the gradient at the pixel location is basically lower than the low one, then you can say that okay, this is definitely not an edge pixel. So you will call it a non-edge pixel. And similarly, now the problem, so these two are very decisive. What happens when it's greater than high and lesser than low? But what happens in between? That's the interesting part. So suppose you have at a pixel location, you find out the gradient value and see that it's greater than the low threshold but lesser than the high threshold. What do? You have to take a, this is a heuristic again. So all these mechanisms, everything basically is a heuristic. So similarly this is also a heuristic. So you treat it as an edge pixel if it is connected to an edge pixel. Okay, so for example, if we again look back at this image, we were missing some edge pixels here. So suppose here there's a point which is dark, which got erased due to the NMS step. What we do is we'll first see that whether its gradient magnitude is in between that low and high. Now, if that happens really, suppose it's in between that low and high, then what I'll do is I'll try to see its neighbors. Okay, if in its neighborhood there is any pixel that is a strong edge, then you call it a strong. Then you again call it a edge pixel. Otherwise, you remove it. So in that way, basically, you are again. So what was the first step? The first step that was that you blur the image and remove the noises. Second step, you roughly detect the edges using a Sobel operator or any edge detector. Third step, you know that there are many not noisy, there are many thick edges that were detected by the in the second stage, and now you basically require fine edges to describe the image. So you do the NMS step to get rid of the the thickness of the edges and get fine lines for them. And the fourth one is that due to this NMS step, we are losing out on some of the you know some of the edge pixels. So what we do is we do this hysteresis thresholding, and this gives us back many of the most of the edge pixels. So now the at the end the image looks something like this. So this is much more detailed, which consists of many of the edge most of the edge pixels. So at the end of this step, what we again, you'll realize that this is way beyond the functionality of Sobel. So that is kind of where the, I mean, greatness of Canny detector lies. So it's doing so much better by doing all these steps. It's actually doing so much better in detecting the true edges. So code wise, yeah. So
I have a question on the non-max.
yeah,
So
go
sure,
on.
thank you. Uh, if you have a thick edge,
Hmm.
uh, it depends upon the window you're looking for the
Correct.
non-max.
Correct. Correct.
Will,
Correct.
will it not find in locality like there is a lot of it may not suppress uh,
Um,
enough.
Yeah, so that's again, that's dependent on how you set your locality. So it has to be, it can't be too big and it can't be too small. So that is why people have heuristically seen that probably locality of 3 pixels works the best. That is why they choose that. Otherwise, if you if we go here, suppose you pick something too big, then also that is problematic. If you choose something too small, then also you don't gain anything. So these things are heuristically fixed.
Okay. Yes. So when I pick within the 3 by 3,
Hmm.
do I only keep it if it is the maximum in that
Correct.
3 by 3
Correct.
window?
Correct. Yeah. Yeah.
Only if it is the
No,
maximum in the 3 by 3.
not in the entire 3 by 3 window. So as I said, if you remember this particular diagram, it actually
Yes.
looks at not the, so imagine there's a 3 by 3 window around this circle. So it's not always looking at the entire neighborhood. Based on the orientation of the edge for the central pixels, take this point to be the central pixel. So depending on the orientation of the edge, suppose if the edge angle is somewhere around say 47 degree, okay, so then it will fall within this bin. And now this bin, the way it's structured, this bin which is called 1, which is numbered 1, suppose, based on the shape of this bin. So if you look at it, it's looking basically at one of the diagonals. So if you imagine a 3 by 3
Yes.
window around it, it's looking at the diagonal elements. So here you have the central pixel, here you have the, the top pixel and bottom pixel. Similarly, based on if your edge orientation is suppose 90 degree only, so you'll fall within this window
Okay.
called
Thank
this
you.
this bin called 2. So then you look at the top one and bottom one. That is how you
Okay. So,
understand.
okay. And then, so it actually first takes the gradient of that edge and then decides
Correct.
which window to look at.
Correct,
Okay.
correct. Gradient and
And
then
then,
the orientation as well. So here basically you look at the orientation.
okay. And then when you do the, on the next step where you
Hmm.
are, you know, uh, finding out whether you are neighboring
Hmm.
a edge pixel.
Hmm.
So each pixel looks at its neighbors, and
Correct.
then if the neighbor is a strong edge pixel,
Correct.
then this also becomes a edge pixel, and
Correct.
that's how
Correct.
it's able to.
No, so
Um,
it looks at the neighbors. At this step, what it will do is just like I said, it will look at the neighbor. Maybe it's a diagonal neighbors or top and bottom and so on. So now suppose these are the three. So you can see the 3 pixels here. So if I zoom it a little bit,
yes, yes,
yeah, there are 3 pixels here. So suppose you are the central pixel, you will see what are the values inside the neighbors. If you are higher than the neighbor, then you'll still retain this particular pixel. Otherwise, you will not retain this. Not retain means you will say that okay, this is not an edge pixel. If it's
yes. On
greater
on the
than,
next step, yeah,
yeah,
on the next step that you
yeah,
had, the
yeah,
after
correct,
this
correct, yeah,
process,
yeah.
you had the low and max,
Correct,
like
correct.
min and max thresholding.
Low and high threshold. Then you will see whatever you said is correct.
Correct.
So yeah.
And
Hmm.
then finally you had the final step
Hmm.
to deduct all the edges.
Hmm.
The canny was doing the, yeah, beyond this step, yes.
Yeah, yeah,
Yeah,
correct.
in this step,
Yeah.
it looks at the neighboring pixel, and
Hmm.
if neighboring pixel is an edge pixel,
Correct.
um, and as long as it is not below low and above high,
If
if
it's
it's in
above
that
high,
middle
yeah,
area,
so let me clarify. If it's above high, it's already an edge. So we were finding
right?
gradients so gradients, if you remember, they are used to find edges. So we want them to be high above some threshold, higher than some threshold. So if it's already high than the high threshold, then it's already an edge pixel. We don't have any doubt about it. If it's lower than the low threshold, that means it's too low. We don't want it. So that we consider it as a non-edge pixel. We say that okay, this is not an edge pixel. Now, what happens? The fun happens when you are in between. So when you are higher than low and lower than high, then there's a dilemma like what happens with those pixels. So there what you are saying comes into picture. So if that particular pixel, if the gradient is in this range in between the two thresholds, then you'll try to find out if it's connected to an edge pixel already. If yes, then you'll treat it as an edge pixel, otherwise you'll treat it as a non-edge pixel and you'll eliminate it.
Okay, thank you. It makes sense. Thank you.
Yeah. Okay, so this particular step we were looking at. So yeah, then comes the linking and thresholding step. So here you can see that this function does the thresholding, and the low value is kept as 0.5 and high value is kept as 0.9. And so I'll skip this one in the interest of time, but once you go through it in a bit more detail, you'll see that whatever I said is implemented here. So you basically consider whenever you have a strong edge, then it's fine. Whenever it's the value is lower than the low threshold that is there, we discard the pixel, and if it's in between, then it will try to find a path towards the strong edge. If that exists, then we treat it as an edge, otherwise not. So this threshold step basically completes your edge detection. Yeah, whatever you are trying to detect, and you'll see once you go up and compare this with what Sobel had found out originally, you'll see that this is much better. This is much more detailed, much better. So that is why Canny edge detector is one of the very seminal edge detectors that is available out there. So now let's very quickly, we have very less time. So a little bit 5 minute, let's talk about SIFT. So SIFT is what? SIFT is a feature detector in easiest words. So basically when humans see an image like this, they kind of in their minds they form some sort of notion about what is going on in that image. So similarly, we do it in some way, and machines have to do it in another way. So machines, what they do, how we make machines understand what's going in inside an image is through features. Features are basically vectors of continuous numbers, that continuous values that kind of give the, so the computer will know like what a particular feature vector means. So a computer knows that suppose you'll have a vector for this leg of a table. So when the computer sees that vector, the computer knows that there's a leg of table leg in this picture. So something like that. So this is how computers process images through finding features for the different objects that are present in the image, different areas that are present in the image. So this, you'll see that when you go inside deep learning, inside CNNs and all, you'll see that everything operates in that way. So feature finding is one of the centrally important steps in deep learning, how deep learning models understand images and all. So this is a pre deep learning era feature extractor feature. This algorithm basically finds features for you inside the image in a non-deep learning way. But yeah, this, if you go through it, it's a very interesting one. But in the interest of time, I'll very quickly go through the first step. So first step is what? So I hope if you go through the lectures of the whatever lectures were taught by professor in the last week, you'll already understand what are these four steps. So the what is the step? What is the first step? You want to find interesting points in the image. Okay, so you want to find points in the image which are telling something about the image. So it's something like this. So given an image of this house, you are trying to find out what elements are there in the inside this image which convey interesting information about this image. So you want to find out these interesting points. So that is done through this particular step called scale space extrema detection. So what you want to do, why you want to do this is because um, these features, whatever in this image, whatever we want to find out, whatever interesting points we want to find out, they should be irrespective of the orientation of the image, whatever, I mean, whether it's a color image or grayscale image, etc. So suppose this window is interesting to us in spite of anything, even if the house was rotated, the image of the house was rotated, it was translated a little bit, whatever, this would have been an interesting point to us because this tells us something about the image. So that is why we want to find out interesting points. We want to find out points in the image. How they are interesting? They are interesting if they are, they basically you do transformations to the image, and then even after those transformations, if the point remains interesting, then we pick it up as some of the interesting points. And once these points are detected, then go through these step 2, 3, and 4, I can't, in the interest of time, I don't have time to explain them, but through these interesting points, basically, you'll get vectors to describe each of them. That's the end goal of SIFT. So, very quickly, what's going on here? So, we want to compute something called scale space as a first step. So, scale space is what? Scale space is basically you have a Gaussian, you have a Gaussian filter with a fixed sigma, with a fixed standard deviation, which you convolve with the image to get something called the scale space, which we call L of x comma y comma sigma. So Gaussian kernel is given by this formula, which this we have seen before. And so what we want to do is very quickly we want to compute something called DOG. So basically, I hope you have recollect from your previous week's lessons that there's something called Laplacian of Gaussians. So the Laplacian of Gaussians are basically useful in detecting blobs and all. So blob detection basically helps us detect interesting key points. So what we are trying to do here is that we are trying to approximate the LOG, that is the Laplacian of Gaussian, with something called a DOG, which is difference of Gaussian. So what we do essentially here is just I'll go through the math part only. So you have this particular scale space thing, which is a convolution of a Gaussian with the original image. All you have to do is you have to compute this for different values of sigma. So you have an original sigma value which is predefined. All you have to do is just get multiples of it. So 2 sigma, 3 sigma, 4 sigma, and so on. So that will give you new Gaussian kernels basically, and you convolve the image with the difference of these two. So inherently what happens is if you break this up, it's g of x comma y comma k sigma into convolved with I of xy minus again this convolved with this. So this basically gives you, so again as I said, one thing in the beginning of the class, if you remember, as and when I increase this value of k. So originally it was sigma. Now we can have 2 sigma, 3 sigma, whatever. As and when I increase the value of k, the image becomes more and more blurrier. Okay, so basically we are convolving now with this convolution of this with the image, you are getting a more blurrier version of the image. The idea is that you transform the image, go on transforming the image in this way, and even after those transformations, you want the interesting points to be there. So they should not be lost after the transformations. So this is what we meant by scale space. So scale space is what? So you have a fixed, so these are all Gaussian kernels. What happens is that the scale is basically the k value here. So the scale keeps on increasing in this way. So if this was sigma, this has 2 sigma, 3 sigma, 4 sigma, and so on. And now what you do is you take any these two, I mean two successive Gaussians, and what you do is you find their difference. So that is known as difference of Gaussians. So these things are, so if the I mean this is called the first octave, and second octave means your Gaussian kernel has actually shortened a little bit. So I'll just give you examples. So example would look like this, that you can see that this is when you convolve an image with a Gaussian of scale 0, which means there is basically no convolution. It's something like this. As and when you increase the scale 1 means 1 into sigma, scale 4 means 4 into sigma, and so on. You see that the images go on become more and more blurrier. So that is the effect of introducing this. So as and when you go up this side through one octave, the image becomes more and more blurrier. Similarly, what octave means is that this is the first octave where you have a bigger image, and you apply your Gaussian filters and make it more and more blurrier. Similarly, second octave is where you shorten the image a little bit, and it becomes and in that shortened space you make it more and more blurrier, and then there's third octave and so on. So now how do you find the interesting point is you take the so you find the DOGs like this. So on the DOG plane, now the next step comes in the DOG plane. So what you do is, suppose you are a pixel here. So now you'll create a 3 by 3 window around it, and you look at the upper DOG value, upper DOG window and lower DOG window at the same position. So you'll create a 3 cross 3 window everywhere at the around the same pixel location, and now you'll see that you know you'll compare the values around it, in these windows with respect to your central pixel. So how many are there? There are 9 here, 8 here, which makes it 9 plus 8, 17, and again a 9 here, which makes it 26. So this central pixel now has 26 neighbors based on that. So what you do is compare each point to its 26 neighbors. So you take this point and compare it with its 26 neighbors. So it's described here, 8 at the same level, 9 above and 9 below. So select as key point if it's smaller or larger than all these neighbors. So basically if it's smaller or larger than all these neighbors, then it's an interesting point. Otherwise it's somewhere in between. So that is what you do. You take each of these and then you suppose you take this one and you take the one that is above and below, and then you try to find the interesting points from that. So that is more or less what is this this is how basically you find out what are the interesting key points in the image. And so at the end of this procedure, what you have is this image of the house is there, and then once you do this procedure of DOGs and then finding out the interesting points, you'll see something like this. So all these points, basically they are some lines with arrows. So wherever the arrow starts, these are the interesting points, like this. So these are the interesting points that the algorithm actually looked at. And then there are other ways to you know so these are some rough, basically these are rough key points that we detected. So from here you have to make it more and more refined. So those are given by the next steps. So key point localization, orientation estimation, and finally key point descriptor. So these steps you have to go through after this particular step to finally extract features from this. So we are
What what we shall be doing for the topmost scale and the lowermost scale, because we
uh,
have to compare between
what
three.
yeah. So basically, in that case you will take only these. If I understand correctly, then you need a topmost and a lowermost. So
Can we pad it?
yeah, that's a good idea. I mean, I'll have to check that up. I'm not very sure what happens for these boundary cases basically. So either there are two options. One is that you take this and you take the upper one. You don't consider the lower one. And similarly for this one, you don't consider the upper one. So that is, I think, the easiest way that you can go through. Uh, when you don't consider all 26 here, but you just consider whatever is available for you. So yeah, that is probably how it happens, but I'll check and let you know.
Okay.
So this is more or less what we had for this week. So yeah, we'll meet on Friday then once again.
Thank you, ma'am.
Okay,
Thank
thank
you.
you. Thank you.
Thank
Thank you,
you.
ma'am.
Thank you,
Thank you,
ma'am.
ma'am.
Thank you very much.
Thank you.